Here is what happens without a virtual network. You deploy a database. It either gets a public IP visible to the entire internet or it has no connectivity at all. Neither is acceptable. A VNet solves this by giving you a private, isolated network in Azure that behaves like a corporate LAN, but runs in the cloud. A virtual network is your own isolated network boundary inside Azure. Resources you place inside a VNet can communicate with each other using private IP addresses. They are not reachable from the internet unless you explicitly open that path. Other Azure subscriptions, other VNets, and the public internet are all outside by default. You define the address space when you create the VNet a CIDR block like 10.0.0.0/16. That block gives you 65,536 possible IP addresses to assign to resources inside the network. Azure reserves the first 4 and last IP in every subnet, so a /16 gives you slightly fewer usable addresses, but for most workloads that is far more than enough. Almost every meaningful Azure workload eventually needs a VNet. Virtual machines require one. Azure Kubernetes Service runs its nodes inside one. App Service can integrate with a VNet for outbound traffic. Azure SQL Managed Instance requires a dedicated subnet. The VNet is the foundation of secure, production-ready Azure architecture. Understanding it deeply is not optional, it is the prerequisite for everything that comes after. CIDR notation intimidates developers who have not done networking before. Let me make it concrete and practical. The slash number in CIDR tells you how many bits are fixed in the address. A /16 fixes the first 16 bits of the 32-bit IP address, leaving 16 bits free, meaning 2 to the power of 16, or 65,536 possible addresses. A /24 leaves only 8 bits free, giving you 256 addresses. A /8 leaves 24 bits free, over 16 million addresses. For a VNet, choose a private address range from one of the RFC 1918 blocks. The 10.0.0.0/8 block is the most commonly used in enterprise Azure deployments because it gives you enormous room to grow. Start with 10.0.0.0/16 for a small workload, 10.0.0.0/8 if you anticipate significant scale or multiple connected VNets. Here is the critical planning mistake I see constantly. Developers choose a small address space, 10.0.0.0/24, 256 addresses, and then cannot expand it later without destroying and recreating resources. Azure does not let you resize a VNet address space that has subnets in use. Plan large. The address space costs nothing. Migrating a production network because you ran out of IPs is extremely painful. The other constraint is uniqueness across peered networks. If you peer this VNet to another VNet or to an on-premises network via VPN, the address ranges cannot overlap. If your on-premises network uses 192.168.0.0/16, your Azure VNet cannot use that same range. Plan your address space with your network team before committing to it. Subnets are how you segment your VNet into logical zones. Think of a VNet as a building and subnets as floors. Each floor has its own address range and its own security rules. The standard pattern for a 3-tier application is 3 subnets. A front-end subnet for your web servers or app service. An application subnet for your back-end API or middleware. A data subnet for your databases and storage. By separating these tiers into subnets, you can apply independent security rules to each tier. Your database subnet can reject all inbound traffic except from the application subnet on the specific database port. Even if your front-end is compromised, the attacker cannot reach the database directly. Subnet sizing follows the same CIDR logic as VNets. A /24 subnet gives you 256-5 reserved equals 251 usable addresses. For most application tiers, a /24 is comfortable. For large AKS clusters that might run hundreds of pods, you need significantly more, sometimes a /20 or larger. Several Azure services require their own dedicated subnets and cannot share with other resources. Azure Kubernetes Service requires a subnet for its nodes, and if you use Azure CNI networking, pods consume IPs from that same subnet, planet very large. Azure Application Gateway needs a dedicated subnet. Azure Bastion requires a subnet named exactly Azure Bastion subnet. Azure Firewall needs a subnet named Azure Firewall subnet. Azure VPN Gateway and ExpressRoute Gateway each need their own gateway subnet. Design your subnets with these requirements in mind from the start. Network security groups are the primary traffic control mechanism in Azure networking. Every production subnet should have one. An NSG is a collection of inbound and outbound rules. Each rule has 5 components: a priority number between 100 and 4096, a source address or range, a destination address or range, a destination port, and an action of allow or deny. Lower priority numbers when a rule at priority 100 overrides a rule at priority 200. When you create an NSG, Azure adds 3 default inbound rules automatically. 1 allows traffic from within the same VNet. 1 allows traffic from Azure Load Balancer health probes. 1 denies everything else. These defaults are sensible. Nothing gets in from the internet unless you explicitly add a rule to allow it. You can apply an NSG at 2 levels. Attached to a subnet, the rules apply to all resources in that subnet. This is the recommended approach. Attached to an individual NIC, the rules apply only to that specific VM. When both are present, both are evaluated. The subnet NSG runs first for inbound traffic, the NIC NSG runs first for outbound. A practical production pattern for a web application: the frontend subnet NSG allows inbound port 443 from the internet in port 80, and denies everything else inbound. The application subnet NSG allows inbound only from the frontend subnet on specific ports. The database subnet NSG allows inbound only from the application subnet on the database port 1433 for SQL Server, 5432 for PostgreSQL. Nothing from the internet can reach the database, even if all other NSG rules were misconfigured. This is one of the most confused topics in Azure networking, and the confusion leads to real security problems. Let me be precise. Service endpoints optimize the network path from your VNet to Azure PaaS services like storage or SQL database. Without a service endpoint, traffic from your VM to Azure storage travels from the VM to the internet, then to the storage public endpoint. With a service endpoint enabled on your subnet, traffic travels from the VM over the Azure Backbone network directly to the storage endpoint faster, more secure, and you can restrict the storage account to only accept traffic from your VNet. The limitation of service endpoints: the Azure service still has a public IP endpoint. You have restricted who can access it, but the service is not truly private. The traffic still technically exits your VNet's address space. Private endpoints are different in a fundamental way. A private endpoint creates a network interface inside your VNet with a private IP address from your subnet's range. That private IP is mapped to a specific Azure PaaS service, your specific storage account, your specific SQL database. Traffic from your VMs to that private IP stays entirely within the Azure backbone and your VNet. The storage account or SQL database can be configured to reject all public network access. The only way to reach it is through the private endpoint. For sensitive data, databases, key vaults, storage with private data, private endpoints are the right choice. They provide the strongest network isolation available. Service endpoints are acceptable for non-sensitive services where you want performance optimization but full private access is not required. VNet peering is how you connect 2 separate virtual networks so resources in each can communicate with each other using private IP addresses, without any traffic touching the public internet. The classic use case: you have a hub VNet containing shared services, DNS, firewalls, monitoring, jump boxes, and multiple spoke VNets for different applications or teams. Each spoke VNet peers to the hub VNet. Resources in the spoke can reach shared services in the hub, and the hub can monitor or inspect traffic from all spokes. Peering is straightforward to configure. Each VNet needs a peering connection pointing to the other. Peering is directional. You create a peering from VNet A to VNet B and a separate peering from B to A. Both must exist for the connection to work. The most important behavioral characteristic of VNet peering is that it is non-transitive. If VNet A peers to VNet B, and VNet B peers to VNet C, VNet A cannot reach VNet C through B. The network is not routed through. Each peering is a direct point-to-point connection. If you need A to reach C, you must create a direct peering between A and C, or route traffic through an Azure firewall or NVA in a hub that has explicit routing configured. Peering has a cost. You pay for data transfer between peered VNets. Within the same region, it is relatively cheap. Cross-region global VNet peering costs more per gigabyte. For high-bandwidth scenarios between regions, compare the cost of peering data transfer against a VPN gateway or express route, which may be more economical at scale. DNS inside Azure VNets is one of those areas that works invisibly when it is configured correctly, and breaks everything when it is not. Let me explain what Azure provides by default and when you need more. By default, Azure provides DNS resolution for resources within the same VNet. If you create two VMs in the same VNet, they can resolve each other by their hostname, the VM name you assign in Azure. Azure's DNS server at the IP address 168.63.129.16 handles this automatically. You do not configure anything. This default DNS works for simple single VNet deployments. When you need custom domain names or DNS resolution across peered VNets, you use Azure Private DNS Zones. A private DNS zone is a DNS namespace you own, like myapp.internal or database.private, hosted in Azure. You link it to one or more VNets. Resources in linked VNets can resolve names in that zone. You can enable auto-registration so VMs automatically create DNS records in the zone when they start. The important scenario to understand: if you have a hub-spoke topology with multiple spoke VNets and a private DNS zone linked only to the hub, resources in the spoke VNets cannot resolve names in the hub's private DNS zone by default, because private DNS zones are not automatically accessible through peering. You must link the zone to each spoke VNet that needs to resolve it, or use an Azure DNS private resolver to centralize DNS forwarding. Azure DNS Private Resolver is the enterprise solution for hybrid environments where on-premises servers need to resolve Azure private DNS names, and Azure VMs need to resolve on-premises DNS names. It provides inbound and outbound DNS endpoints inside your VNet that you configure as forwarders in your DNS architecture. HubSpoke is the network topology you will see in almost every serious Azure deployment. Once you understand it, you will recognize it everywhere. The Hub VNet is the shared network services layer. It contains Azure Firewall or a third-party network virtual appliance for traffic inspection and policy enforcement. It contains Azure Bastion for secure VM access. It contains a VPN gateway or ExpressRoute gateway for connectivity to on-premises networks. It contains DNS resolvers. The hub is the control plane for your entire Azure network. Spoke VNets are where applications live. Each spoke is isolated: the spoke for the production e-commerce application, the spoke for the development environment, the spoke for the data analytics platform. Each spoke peers to the hub and can reach shared services in the hub. Spokes do not peer directly to each other. All inter-spoke traffic routes through the hub, where the firewall can inspect and log it. The key advantage of HubSpoke is scalability and governance. When you add a new application team, you create a new spoke VNet, peer it to the hub, and they immediately have access to all shared infrastructure, DNS, Bastion access, VPN connectivity to on-premises. No changes to existing networks. No redesign. New spoke, peer to hub, done. Azure Virtual WAN is Microsoft's managed HubSpoke service. Instead of managing the hub VNet yourself, firewalls, gateways, routing, virtual WAN provides a managed hub that Microsoft operates. You connect your spoke VNets, on-premises branches, and point-to-site VPN clients to the virtual WAN hub. For large enterprises with many branches and spokes, virtual WAN simplifies operations significantly. For most cloud-native deployments, a self-managed hub spoke is sufficient and more flexible. Let me save you from the mistakes I see teams make repeatedly, because these mistakes are expensive to fix after the fact. Mistake 1: Too small address space. Developers unfamiliar with networking pick a /24 or /23 and hit capacity 6 months later when AKS pods consume all available IPs. Always use a /16 or larger for your VNet. The address space is free. The migration is not. Mistake 2: Overlapping IP ranges. You create your Azure VNet with 10.0.0.0.16, and then try to peer it to your on-premises network, which also uses 10.0.0.0/16. Peering fails. VPN fails. Nothing can connect. Coordinate your IP address ranges across your entire organization, on-premises and cloud, before you deploy anything. Mistake 3: One flat subnet for everything. All VMs, all databases, all services in one subnet with one shared NSG. You cannot apply different security rules to different tiers. A compromised web server has direct network access to the database. This is the flat network mistake that made breaches easy in the 2010s, and it still happens in Azure deployments. Mistake 4: Skipping NSGs on subnets. Every subnet in a production VNet should have an NSG. Without one, resources in that subnet can receive traffic from any other resource in the VNet on any port. The principle of least privilege applies to networks too. Mistake 5: Not planning subnet reservations for managed Azure services. When you realize you need Azure Firewall later and have no room for a /26 Azure Firewall subnet, you are redesigning your network under load. Add these dedicated subnets in your initial design even if you do not deploy those services immediately. Let me show you what a complete, production-ready 3-tier application network looks like in Azure, using everything we covered. The VNet address space is 10.0.0.0/16, plenty of room to grow. We carve it into 4 subnets. Azure Bastion subnet at 10.0.0.0/27. 32 addresses, the minimum size Azure requires for Bastion. Azure Bastion gives us secure browser-based RDP and SSH access to every VM in the VNet without a single public IP on any VM. This subnet hosts nothing else. The frontend subnet at 10.0.0.1.0/24 is where our app service has VNet integration enabled. This means outbound traffic from the app service routes through this subnet. The application gateway, our web application firewall and load balancer, sits at the edge, receiving HTTPS traffic from the internet and routing it to the app service. An NSG on this subnet allows inbound 443 from the internet to the application gateway, and blocks everything else inbound. The application subnet at 10.0.2.0/24 holds backend VMs or Azure container instances running our API layer. Its NSG allows inbound only from the frontend subnet on the specific API port. No direct internet access to this tier. The data subnet at 10.0.3.0/24 holds private endpoints for our SQL database and storage account. Both services have public network access disabled. The only path to the data layer is through the private endpoint on this subnet. The NSG allows inbound only from the application subnet on the database port. This is zero-trust networking. Every connection is explicitly granted, and nothing has broader access than it needs. Think through the network path before looking at the answer. Both VMs are in the same VNet, so basic routing works. VNet resources can reach each other by default. But subnets can have NSGs attached. If the data subnet NSG has an explicit deny rule, or no allow rule for traffic from the app subnet's address range, traffic is blocked even though the VMs are in the same VNet. The fix: add an NSG inbound rule on the data subnet, allowing traffic from the app subnet CIDR range on the specific port your application needs. This is exactly the right behavior. You want the database tier to reject everything except authorized traffic from the application tier. Active recall: understanding this scenario is the difference between reading about NSGs and actually knowing how Azure networking works.